Welcome to class number 11 of transport phenomena in mesoscopic and nanoscopic systems. And last day we were discussing the Hamiltonian and wave function and eigenenergies, eigen wave functions for a periodic chain of lattice points or periodic chain of atoms. And we showed that the Hamiltonian can be discretized, and in this case if we use the position basis, the Hamiltonian appears to have a tridiagonal form with one main diagonal with one upper diagonal and another lower diagonal. Okay, and then we also discussed that in the case of a periodic crystalline structure, the wave function is mainly given by psi m equals to psi 0 e to the power I k dot dm. This is for the three-dimensional case, the crystalline structure in the real space. In the real space, k is a vector as well as dm is also a vector. Dm is the position of the lattice points. For example, here this is lattice point 1, 2, 3, 4, 5 and 6, and we are using position basis. So this is wave function at position 1 or lattice point 1, then 2, 3, etc. Okay, in the three-dimensional case, the wave function may be given in this form, and the overall eigenenergy or the eigenstate can be solved by solving an equation of this form: E psi m equals to E SS psi m minus 1 plus E0 psi m phi m plus E SS phi m plus 1. And then if we plug this into all this this thing and this thing, we will ultimately get an equation of the form E phi 0, where phi 0 is this constant over here, equals to E SS e to the power minus I ka plus E0 plus E SS e to the power I k a. So this is for a one-dimensional lattice. When we have a three-dimensional lattice, this same equation becomes E psi 0 equal to summation over m h nm e to the power sorry, not e to the power, but summation over m h nm phi m, where this m or this m over here represents all the lattice points or all the atoms which are nearest to the atom or the lattice point for which I am writing this equation. Okay, for example, if I am writing this equation for this fifth lattice point, m would be 6 and 4. Okay, so here the summation would run from 4 and 6. Okay, so in this case of 3D, we have let us consider a 2D system, because 3D is difficult to show in the paper. So I have drawn a 2D crystal structure over here, and if I am considering the fifth point or the equation for the fifth point, then my nearest neighbor would be this sixth atom, this second atom, this fourth atom, and this eighth atom over here. This one is slightly far. We can as well write a matrix element for this atom as well, or the coupling between these two atoms as well, but we will not go into that much detail. We will just assume that the main coupling happens between the nearest atoms. Okay, or the strongest coupling happens between the nearest atoms. So we should consider this atom 2, atom 6, atom 8 and atom 4 over here. Okay, and HNM is nothing but HNM is basically M. Okay, so we'll just come back to this briefly in a moment. Let me actually complete this equation, and so this equation can actually be written as E phi 0 equals to summation over Hk phi 0, where Hk basically has this form. Okay, so we will see an example after we discuss another thing. So we'll see the example for graphene with this kind of Hamiltonian, or with this kind of representation of the eigenenergies of the system. But before that, let us discuss another thing. So before this class, or in the last class, we basically discussed a chain of similar atoms which are basically connected together in a periodic fashion. So we had this periodic chain of atoms like this. Again, this is a hypothetical case. Now we might have two kinds of atoms in a system. For example, the compound NaCl, sodium chloride, which is a common salt or table salt. Okay, so here sodium atoms and chlorine atoms are present. So some of the atoms of sodium atoms will be chlorine, and some other atoms may be sodium also. But I think the next nearest atoms of sodium in the crystalline arrangement are always chlorine in this case. Anyway, or let us say something like gallium arsenide. Again, gallium is surrounded by arsenic atoms. So it might happen that there are 2 or 3 or 4 kinds of atoms in a given compound, and how to basically write the Hamiltonian matrix for this kind of structures. So let us assume that there are 2 kinds of atoms in our system, so one blue and one red over here. And this blue atom we basically call the wave function at the, or the eigenfunction value at this position of the blue atom by 1a. So we call this entire unit as 1, this entire unit as 2, this entire unit as 3, because now we have the concept of unit cells instead of individual atoms. Now the unit cell contains 2 atoms, 4, 5 and 6. Similarly, this is 1a, 2a, which is the wave function at the position of the blue atom, 3a, 4a, etc. And the wave function at the position of the red atoms, we can write it as 1b, 2b, 3b, and 4b. Now note that the coupling between these 2 atoms, okay, is very different compared to the coupling between these 2 atoms. Okay, so for example, this atom and this atom belong to a unit cell, the same unit cell. This atom and this atom belong to different unit cells. Okay, so let us say that for this atom here, this atom number 3, this coupling is basically different compared to this coupling. Okay, so we write the coupling between atoms in a unit cell as let us say ESS. So let me just denote it here. This coupling we call it as ESS, and this coupling between let me denote at another location so that it is more clear. This coupling we call it as ESS dash. Okay, so how the Hamiltonian matrix would look like now? So if we write the Hamiltonian matrix H, it would now look somewhat like we have these atoms here, or wave function positions 1a, 2a, then 1b, 2b, sorry, not so this is 1b actually, this is 2a, and then 3a, 3b, and so on. Okay, and first we have to write the first row corresponds to the equation for wave function at the first atom in the first unit cell. The second row corresponds to the equation for the wave function of the second atom in the first unit cell. Similarly, the third atom corresponds to the equation, the third row corresponds to the equation for the first atom in the second unit cell, and the fourth row corresponds to the equation for the second atom in the second unit cell. Okay, and so on. So now this term over here, this is the coupling between coupling of the first atom in the first unit cell with itself, and we write it as E0 just like before. The second one is basically the coupling between the first and the second atom in the first unit cell, that is coupling between these two atoms. So as I said earlier, this term is basically ESS. I write it as ESS over here. Now the coupling between these two atoms I have to consider, because this atom is the next nearest neighbor of this atom, and the coupling between these two atoms, as I said, is ESS dash. Okay. Sorry, in the first row all other elements are 0 basically, because I am writing the equation for this atom, so this atom is not directly coupled to this atom over here. Okay, so the next row is the equation for this atom, the wave function at this atom, and these two are basically coupled, and this is ESS. Now this term basically corresponds to the coupling between the coupling of this atom with itself, so this is E0. Then this position corresponds to the coupling between this atom and this atom, the wave function between these two atoms over here, and this is ESS dash. Similarly, this row corresponds to the equation for this atom over here, and there is no direct coupling between this atom and this atom, so the first element is 0. Then this for the second element, it's the coupling between this atom and this atom over here. Okay, so this is ESS. Now this third element, this is the coupling between coupling between this wave function with itself, so this is E0. This is actually ESS dash, because the coupling between these two far away atoms. Okay, and then this fourth position, so I should write it as slightly far away position. This is 2b, 3a and 3b. Okay, so 0 0 0 0 0 0, and then this element represents the coupling of this atom with this neighboring atom. Okay, so this is basically ESS 0 0. Then this row corresponds to the equation for this atom over here. So there is no coupling of these atoms with these two atoms. So the first two are 0. The third one corresponds to the coupling of this atom with this atom over here. So this one is ESS. This one is the coupling of this atom, the wave function of this atom with itself. So this is E0. Then this element over here represents the coupling of this atom with this atom over here. So this is ESS dash 0. And likewise we can continue this matrix. So the important thing to note here is that suppose we write this wave function here as psi 1a, psi 1b, psi 2a, psi 2b, etc., etc. Now the important thing to note here is that suppose we write the equation for this wave function at this atom 2a. So what will we get? We will get, let me write the complete equation. So E psi 2a, so E is the eigenenergy, equals to, so let me go to the previous page. So let me just note down the equation from here. So ESS times psi 1b, E0 times psi 2a, and ESS times psi 2b. Okay, so let me write it here. ESS dash psi 1b plus E0 psi 2a plus ESS psi 2b. So now note that this equation cannot be solved by using a equation of the form psi n equals to phi 0 e to the power I k dot, and not dot because this is one dimension, so I k dot NA. And the second thing is that Na is not defined in this case because the atomic spacings are different. For example, the spacing between these two atoms over here is different compared to the spacing between this atom and this atom. Okay, so an equation of the form of this form does not make sense, and also this above equation, this equation cannot be solved by taking that form because this ESS dash and ESS are different. Earlier what happened is that these two were the same, so their coefficients or this exponential parts basically summed up to give you the cosine term. Now it is not possible because the interatomic distance is also different, and these two terms are also different. So what to do? So here what we do is that we treat these two as a single unit cell. these two as a single unit cell, and we define submatrices. Okay, so when I say that we define submatrices, it means that I define smaller matrices within the larger matrix. Okay, so let me rub this part and write 2a over here. Now I define this unit cell just as I said that 2a is my unit cell, 1a is also 2a 2b is one unit cell, 1a 1b is another unit cell. Okay, and here also 1a 1b is one unit cell, and 2a 2b is one unit cell. So this I call as the first unit cell, and this is the second unit cell, and this is also the first unit cell, this is the second unit cell. Now what is the coupling of the second unit cell with itself? So this matrix defines the coupling of this second unit cell with itself. Which matrix defines the coupling of the second unit cell with the first unit cell? So it is this is the coupling between of the second unit cell with itself. Which matrix defines the coupling of the second unit cell with the first unit cell? So this is the matrix which defines the coupling between the second unit cell and the first unit cell. And which matrix defines the coupling between the second unit cell and the third unit cell? This is the matrix which defines the coupling between the second unit cell and the third unit cell. Now note that the nth unit cell should only be coupled to the n-1th unit cell and the n+1th unit cell. Okay, so when we define unit cell, we also define the next nearest neighbor, that is this unit cell over here, the fifth unit cell should only be coupled with the fourth unit cell and this sixth unit cell over here. Okay, so okay, let me I just accidentally rubbed this part. So this is the submatrix which defines the coupling between second and third unit cell. Okay, so when I now write the equation, I write the equation of the entire unit cell instead of writing the equation for a definite atom. Okay, so let me pick the second unit cell and write the equation for the complete second unit cell. Okay, so let me just write this matrix as H22, which is the coupling of the second unit cell with itself, and let me see what this matrix was. So this matrix over here, this matrix over here, so the matrix which defines the coupling between unit cell 1 and 2, this one was 0 0 0 ESS dash, and the matrix which defines the coupling between 3 and 2, this is ESS dash, sorry, this is 0 ESS dash. Let me just go back to this. Okay, so Okay, so it's here ESS dash 0 0 and 0 over here, and we also define a vector for the wave function, which is basically let me write it as gamma. Gamma 2 is basically phi psi 2a and psi 2b, and the entire matrix, okay, for this basically reads so I will write it in the form of gamma. E gamma 2 is equal to h1 to gamma 1 plus h2 to gamma 2 plus h3 to gamma 3, where gamma 1 is basically psi 1a, psi 1b, and gamma 3 is basically psi 3a, psi 3b. So if you want to understand this, just go back to this matrix format, and you can see that for these two rows, this matrix is basically, this matrix over here, submatrix, is basically multiplied by this submatrix over here. Then this submatrix over here is basically multiplied by this submatrix over here, and this submatrix will be multiplied by, I have not written this to here, but it should be psi 3a, psi 3b. So this matrix would be multiplied, this submatrix over here would be multiplied by this submatrix. So I hope that I have convinced you that the equation I have written is basically correct. So now how to proceed from here? So we note that this gamma 1 is the wave function corresponding to the first unit cell, gamma 2 is the wave function corresponding to the second unit cell, and gamma 3 is the wave function corresponding to the third unit cell. So what we do now is that we write this gamma in as phi 0 e to the power I k n a, where this a is basically the distance between two unit cells. Okay, so in a is the distance between two unit cells here, so I will write it here. A is the distance between two unit cells. So now what we get is basically E. Now one thing I would like to state here is that this phi 0 over here, this is also a matrix. Okay, 2 cross 1 matrix. Just don't confuse that this is a number, but this is a vector actually. So this is a 2 cross 1 vector. Okay, so E phi 0 is equal to h1 to phi 0 e to the power minus I k a plus h2 to phi 0 plus h3 to phi 0 e to the power I k a, which is so E is basically equal to so we have to write it as E phi 0 because phi 0 is again a matrix. E phi 0 is equal to h2 to so actually let me write the complete expression over here. So E0, E0, ESS, ESS. So this is basically h22 plus what is H12? So this is 0 E S S dashed 0 0 e to the power minus I k plus 0 0 E S S dash 0 e to the power plus I k a. Okay, so here this one is a 2 cross 1 vector. Okay, and so we also have to multiply this matrices by phi 0. Okay, so to find out E, we have to just find out the eigen energies of this equation. So how do we do that? We just do a plain and simple determinant calculation, that this determinant of this matrix E0 minus E, E0 minus E, ESS plus ESS dash e to the power minus IK ESS plus ESS dash e to the power plus IKA, this is equal to 0. So it's a plain simple way of finding out eigenvalues. So this basically gives us two values. So E0 minus E square, this is equal to this 2 is ESS square, this 2 is ESS dash square. So let me write it over here, ESS square plus ESS dash square, and then this term with this term and this term with this term, they give rise to, let me write a second bracket here, SS ESS dash e to the power IKA plus e to the power minus IKA. So this is equal to ESS square plus ESS dash square plus 2 ESS ESS dash cos KA, and we have E equals to E0 plus minus because when we take the square root of this side, we get a plus minus over here and then a half over here. Okay, so plus minus ESS square plus ESS dash square plus 2 ESS dash cos KA whole to the power half. So we note that we get the solutions of two bands over here. So one with plus sign, this plus sign over here, this gives rise to an energy band, and another with minus sign over here, this gives rise to another energy band. And for the one with plus sign, that is this one, the bands actually, the energy actually decreases as one moves away from k equal to 0. So let me draw this complete picture over here. So this is the E versus K diagram, and this point is K equal to 0. And for this plus sign over here, the bands actually, the energy actually decreases as one moves away from the K equal to 0 point, so somewhat like this. And for this minus sign over here, the energy actually increases as one moves away from this K equal to 0 point. Okay, so we have two bands as the solution. Now your task is basically to find out the eigenvector of this equation. The eigenvector of this entire equation over here, that is the eigenvector of phi 0, and comment on the constituent orbitals of the first and the second unit cell to make up the entire wave function. Okay, so let me write it here. Find out the eigenvector corresponding to the matrix equation for one unit cell and comment on the constitution of the eigenvector. Okay, eigenvectors actually, because there are two eigenvectors here in terms of psi 2a and psi 2b. Now let us discuss the practical case of an important 2D material, which is known as graphene. And as you know that graphene, even a few years back, had attracted immense attention among the researchers. And even today people are trying to figure out various properties of graphene and what people can use it for. So graphene is basically nothing but it is a sheet of carbon atoms which are arranged in a periodic fashion to form a crystal structure. Of course, this is a two-dimensional material, and the three-dimensional form is known as graphite. So if you stack many graphene sheets in proper stacking arrangement, you would get graphite. And one of the methods of making a graphene sheet is basically it is known as a scotch tape method, where you put a tape, adhesive tape, on the top of graphite and you just pull it back. So the adhesive gets stuck to that graphite surface, and when you pull it back, it basically tears one graphene layer from the surface of graphite. Okay, so graphene basically has a hexagonal arrangement of carbon atoms, and there are 6 atoms at the 6 corners of the hexagon. For example, there is one atom over here, then this atom is already shown here. There is one atom over here, one atom over here, one atom over here, and one atom over here. Okay, so 6 atoms in this hexagonal cell. And now note that we have to first define the lattice structure of this graphene. Otherwise, if we don't define the lattice structure, we do not know the lattice vectors, and hence we do not know the Brillouin zone. And as you know, the Brillouin zone is very important in finding out the energy dispersion relation in a semiconductor or in any material. Okay. So first of all, let us define the unit cell. So can we actually take a single graphene atom and define the unit cell? The answer is of course no, because all the atoms, so there are, as I said, 6 atoms, one over here, this is the second, third, fourth, fifth, and sixth. Okay, so now not all the atoms in this, among these 6 atoms, actually sees the same environment. Okay, so this means that if I only define this atom to be inside my unit cell, I cannot describe the condition of this atom over here, because this atom over here and this atom over here, they see different structure and they see different atomic arrangements. Okay, so if I basically keep only this atom in my unit cell, I would not be able to describe this atom over here. Okay, now if you ask me that why this atom and this atom sees different arrangement in the crystalline structure, the answer is that this atom over here sees two other atoms, uh, this one and this one towards its right, and one other atom, that is this one, towards the left, and this atom sees two atoms towards the left, this one and this one, and one atom towards its right, that is this one. So the environment seen by these two atoms are not the same, but they are basically connected by symmetry arrangement, you may say. Okay, so that is why this atom, the environment seen by this atom, or the situation of this atom over here, cannot be described by this atom over here. So we need both of these atoms in the unit cell, and therefore the unit cell here basically consists of these two atoms. Okay, so this is one unit cell. Let me use a different color other than black. So this is one unit cell, and this is another unit cell, and similarly we have an atom over here. This is another unit cell, and then we have another atom over here. This is another unit cell, and so on. Okay, so now that we have defined unit cell, the lattice vectors, or the lattice translation vectors, which make up the intercrystal structure, are basically defined as the vectors that can take one unit cell to another position within the crystal structure, such that that unit cell sees the same environment as before. Okay, so here we basically define this lattice translation vectors to be this vector a1, this is the conventional vector, this vector a1, and this vector a2. Okay, so if we start from here and if we move by the vector a1, we would basically reach this position. If we start from here and if we move by the vector a2, we will basically reach this position over here. Okay, now what is a1 and a2? So it is not really difficult to calculate. We just have this triangle over here. This is a right angle triangle, and this angle is 60 degrees. Okay, and we define the distance between two atoms in a unit cell as a0. So this distance is basically a0. Okay, so, and as I said that this angle here is 60 degrees. So how do we find this entire distance over? So this distance from here to here, it is basically a0, and this distance from here to here, it is basically this one is a0 cos 60 degree, which is half of a0. So this total distance is basically 3 by 2 a0. So this distance is basically 3 by 2 a0, and this distance over here, this is a0 sine 60 degree, which is root 3 by 2 a0. Okay, so this a1 vector is basically 3 by 2 a0 x cap, where x cap is the unit vector along the x direction, plus root 3 by 2 a0 y cap. Similarly, this vector a2 over here is 3 by 2 a0 x cap minus root 3 by 2 a0 y cap. Okay, Now in three-dimensional space, we have to have three vectors to define a structure, although this is a two-dimensional layer. But still, to calculate the Brougham zone and everything, we need another vector to define, which is along the z direction, because these two vectors lie in the xy plane. So these two vectors define the xy plane basically. The third vector must lie in the z direction, and because this is a two-dimensional layer, we call this third vector only as z cap, the unit vector along the z direction. Now when we need to define Brillouin zone, how do we find the reciprocal lattice vectors? So the reciprocal lattice vectors are basically B1 equals to 2 pi A2 cross A3 divided by A1 dot A2 cross A3, and A3 is basically z cap, and B2 is basically 2 pi A3 cross A1 divided by A2 dot A3 cross A1. Okay. Now the third vector, we do not need the third vector because it is basically perpendicular to the xy plane, but I am still writing it for convenience. Okay, so these are the reciprocal lattice vectors. Okay, and what is the utility of the reciprocal lattice vectors? They are used basically to construct the Brillouin zone, or the first Brillouin zone of the structure. And as we know that all the vectors that reside in a particular band reside in the first Brillouin zone. Or if we want to compute the total charge density, wave function, etc., we have to consider only the first Brillouin zone. Now so your task is basically to prove or find out the first Brillouin zone of graphene and show that the reciprocal lattice of graphene also consists of hexagonal crystal structure. Okay, so I am just stating it here that let me write the expressions actually. So I am not doing the computations, but if you do the computations, this would basically become pi divided by a x cap plus pi divided by b y cap, and this is equal to pi divided by a x cap minus pi divided by b y cap, where a is equal to 3 by 2 a0 and b is equal to root 3 by 2 a0. Okay, and this vector is not needed because it is actually perpendicular to the xy plane, and xy plane in the reciprocal space. And since graphene is a two-dimensional structure or a 2D layer, this third direction in the Brougham zone, in the Brillouin zone, does not really matter, because all the k vectors that would reside in graphene would actually belong only in the xy plane. Okay, it would not, the k vectors residing in graphene would not would not be directed along the z direction, because along the z direction the electrons cannot flow. So no electron wave function would be directed along the z direction, or would flow along the z direction. Okay, so that is why this is basically useless. Okay, so let us do up to here today. So in the next class we will be discussing about the energy bands of graphene near the Fermi level, and about graphene armchair and zigzag nanotubes. Okay, thank you everyone.